Hey guys, Professor Brown here. Welcome back. I am going to give us a little intro today on some really basic stuff having to do with the electrocardiogram or ECG. What I'm going to talk about is very rudimentary. We're going to be showing kind of what we consider the canonical formation, just a real basic ECG trace. And I'm going to show you a couple of what we call the intervals that can tell us a little bit about how electricity is moving through the heart. So again, this is going to be very introductory, but hopefully it'll give us what we need to kind of get started thinking about ECG. All right, so the first thing we need to do is actually draw one. So let's look at the waves. I've got some graph paper here that is typical of ECG paper. This is if you're doing this on old school and recording it with a pen on paper like they did back in the day. It would look something like this. Of course, now we almost always do it digitally, but it's still going to be printed on this grid background. Okay, and there's three waves we need to look at, and each wave takes a certain amount of time. So we're always going to be looking at time here on the x-axis, and on the y-axis we're looking at kind of the intensity or amplitude of the wave, which is going to be measured in millivolts. So this way it's going to be amplitude, which is going to be measured in millivolts. Of course, time is going to be measured in seconds, or in this case, fractions of a second. So each of these little boxes that we see here, each small box, so we'll come up here and just outline one. Each of these small boxes is about 40 milliseconds, or 0.04 seconds in duration. We're not really going to be worried about the y-axis now, because for my students, the pathologies that we're going to be thinking about are problems with the cardiac conduction system that are going to elongate certain sections. So we're really focused on this time dimension down here. So there are three waveforms we need to concern ourselves with. The first is the P wave, and a normal P wave should take about 110 milliseconds, which is just under 3 boxes wide. So if our P wave were to start right here, it would end just under 3 boxes later, so about right here. P waves tend to be somewhere in the neighborhood of 2 little boxes tall, so our P wave would look something like that. Now, the next waveform, so this is P. The next waveform is the QRS complex. This has to do with depolarization of the ventricles, whereas the P wave is depolarization of the atria of the heart. And the QRS complex is going to be really tall because it has to do with the ventricles. So it's going to end way up here somewhere. But because of the cardiac conduction system, which you may have heard of before, the depolarization of the ventricles is going to occur very quickly. As a matter of fact, if it starts, say we'll let it start right here just to make things nice and even, it's going to be just around 2 little boxes wide, so it's only going to be about yay wide. So to get the whole QRS complex, there's the Q wave. We'll go all the way up here for the R wave, and then all QRS, and it's a little bit crooked, but you get the idea. This is kind of hard to draw. Now there's going to be a little time between when so here's Q, here's R, and here's S. Now, depending on the lead configuration of the ECG you're looking at, you might not see all three of these waves. Using the standard kind of A&P lab 3-lead EKG, as a matter of fact, the Q wave is often absent given the lead configuration that we would use in a typical A&P classroom. All right, now finally, the last waveform we're going to concern ourselves with is the T wave, and it's going to start somewhere about here, so roughly 4 boxes after the end of the S wave, and it's going to take roughly 1, 2, 3, 4 boxes. So the T wave is going to be about that long. So we're going to have a little bit, and like I said, this is not every lead configuration. This is just kind of a standard, like a lead 1 configuration that you might see, and the T wave is going to be a little bit taller than the P wave, so it's going to be about 3.5 boxes tall, so it needs to come up about yay far and then come back down, and then we'll have something like this. So this is the T wave, and then we have this period between the end of this T wave and the beginning of the next P wave. 1, 2, 3, which would be something like that, and then QRS, and again, sorry for the poor drawing quality, but you get the idea. This period between heartbeats is what we refer to as the quiescent period. quiescent period. And this is the time when there are no action potentials being generated in the myocardium of the heart. It's essentially the space between heartbeats. So these are the basic waveforms. Now, there are a couple of what we call intervals, the time it takes to go through one syncytium of the heart or another, that we also need to concern ourselves with. The first of those are what we refer to as the PR interval, which actually goes from the beginning of the P wave to the beginning of the QRS complex. Now, it's called the PR interval because this R wave is the predominant wave of the QRS complex, and it's always going to be there. The Q wave may or may not be present given the individual that you're examining and the lead configuration you're using. So even though it's called PR wave, it actually ends at the beginning of Q if Q is present. If not, it would be at the beginning of the R wave. Okay, so this is the PR interval. And the PR interval is going to tell us something about how long it takes the action potential to travel through the atrial syncytium. So this is really telling us about distance from the SA node to the AV node. And again, the handwriting is awesome with this tablet I'm using, this writing tablet. Okay, that's the PR interval. It's going to tell us from the SA node through the AV node. Now there is another interval which goes from the beginning of the QRS complex to the end of the T wave. I'm sorry about that noise, I just got an email. And this is called the QT interval. So QRS is when the depolarization begins in the ventricular syncytium. T is repolarization. So from Q to the end of T is going to tell us about movement of the entire action potential through the ventricular syncytium. So this is everything from essentially the AV node through the ventricles. So the waveforms we're going to concern ourselves with are P, QRS, and T, and then the intervals or periods we're concerned with are the PR interval from beginning of P to beginning of QRS, and then the QT interval from the beginning of QRS to the end of T. Now, why are we concerned about these? Well, mainly because deviations in the normal time for these intervals can tell us if there is a blockage in the cardiac conduction system. So I'm going to come over here and we're going to hide this layer, and we're going to talk about what can happen if that deviates. So the P wave should normally be just under 3 little boxes. So 1, 2, 3, and then QRS should take about 2 boxes, so 1, 2, and then we should have 4 block interval, and then 1, 2, 3, 4 for the T wave. So we would have P, and then a little bit of time, and then QRS, I drew that a little bit short, and then a T wave. Okay, that's normal. So the PR interval from here to here should be somewhere between 0.12 and 0.2 seconds. Okay, so keep in mind 0.2 seconds is going to be about 5 little boxes. Okay, so it should be less than 5 little boxes. In somebody with what we call a first degree AV block, that is, there's something wrong with the AV node or the junctional fibers leading into the AV node, and our signal is not making it into the ventricles as it should, and there are lots of things that can cause these blocks, various pathologies, disease conditions. Lyme disease can cause a first degree AV block. We're going to see prolongation of this. So what we're going to see often is the P wave will proceed fine, but then there's going to be some delay before the beginning of the QRS complex. So what we would end up with is a PR interval of much longer. So in this case, the PR interval is 1, 2, 3, 4, 5 little boxes. So that's just on the long end of normal. So that would be 0.2, or we might see something. So here's a P wave, and then elongated thing here, and then QRS. And again, sorry for the poor writing. It's hard to do on this. So now we go here to about right here, and that's 1, 2, 3, 4, 5, 6, and change little boxes. So now we have a PR interval of around 0.24 seconds, which is quite elongated. So that would be a very simplified. So cardiologists, if you're watching this, don't fuss at me. This is for introductory A&P students. Okay, so that's an elongation of the PR interval. Now, again, let's draw a normal ECG. So we'll start up here. Okay. It is invisible. I know it's invisible and can't be edited. I'm trying to make it visible. Here we go. So it goes, I made it visible. There. Super. So we need to go 3 blocks, 1, 2, just under 3 for P, 2 blocks for QRS, 1, 2, 3, 4, and then 1, 2, 3, 4 for T. So here is our P wave. Let's see if I can make this QRS nice and neat. 1, nope. 2, 3. Wow, I am terrible at this. Okay, there we go. So there's our nice normal or normal-ish ECG. If we have a prolonged QT interval, so from here to here takes too long, we might see, usually, there are lots of things that can cause this. They usually fall under the category of what we call an infrahissian block, meaning it starts at the AV bundle or bundle of His and extends along somewhere distal to the AV bundle. So a good example of that, and one that I use in my classes, oops, got another email, sorry about that, is what we call a bundle branch block. And that's a situation where one of the bundle branches, usually the left bundle branch, has been impaired, say by endocarditis, secondary to some sort of infection, or maybe you have coronary artery disease. There are, again, lots of things that can cause these, but we'll see that the P wave, 1, 2, just under 3, is fairly normal. But when we get to the QRS complex, and 2 of the leads in a 12 lead especially, but you can see it in multiple leads, the QRS is going to be prolonged. So Q is going to kind of come down like this, and then we get a real lazy R wave, and then S extends so far that we kind of lose the T wave. So we get in something like this. And so our QT interval now goes from here all the way out to here. So we can see that it's 1, 2, 3 blocks longer. So we've extended the QT interval from its normal. It should be 0.44 seconds, roughly, or about 10.5 or 11 blocks wide. Is that 11 blocks? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I drew it wrong. It should go to about right here. That would be a normal QT interval. Now we've gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 blocks. So we've gone an extra 120 milliseconds. Okay, so we've gone to 560, 0.56. Okay, and that's due to this, primarily the elongation of the QRS complex. Okay, so the things that I want my students to remember, and that's really who I'm making these videos for, you should be able to draw and label these things. So draw the P wave, the QRS complex, the T wave, and label on them where the PR interval begins and ends, where the QT interval begins and ends, and then the quiescent period, the period between the heartbeats. All right, well, that's going to be it for today. I hope that helps, and I'll see you next time.